Newton's law of universal gravity. And it is exactly what it says it is. It's universal. What that means is all objects exert a gravitational force on all other objects. It says all. Everywhere in the universe. Now we usually apply this law to large objects like planets and stars, but it can apply to calculators and baseballs and pencils. For example, if you have a baseball in your hand, it exerts a gravitational force on the moon, and the moon exerts a gravitational force on that baseball. They exert a gravitational force on each other. All objects, whether it's people, anything with mass, exerts a gravitational force on anything else with mass everywhere else in the universe. So as I sit here or as you sit there, you're exerting a gravitational force on the planet Pluto, if you call Pluto still a planet. You exert a force on all planets in our universe or in our solar system, all stars in the universe. Everything, everywhere in the universe exerts a gravitational force on everything else in the universe. Now mathematically, we can calculate these forces with this equation right here, which Newton discovered. The force of gravity, and a lot of times it'll say F sub g for the force of gravity, equals big G, and big G is a universal constant. It's not 9.8, that would be the acceleration due to gravity on the surface of the Earth, but it is 6.67, as you'll see down here lower. It's universal in standard units, 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. So once again, if you're on Mars, the Martians use that value for G. If you're on Venus, the Venetians use that value for G. Well, you could have different units for that, but it's a universal constant that applies everywhere in the universe. So the force of gravity is big G, that constant, times the product of the two masses involved. There are always two masses involved, whether it's the Earth and the Moon, or the Earth and the Sun, or a baseball and the Moon, or a person and another person. There's always two masses that are exerting a force on each other. Another thing that's important here is that you divide by the distance between the two objects squared. So R doesn't stand for a radius, it stands for a distance between two objects. I'll circle that. But what's important about this as well is that that's measured from center to center of the two objects in standard units of meters. So I'll give you an example here in a few seconds, but let me give you another diagram here to think about. This diagram represents the gravitational field surrounding the Earth, the three-dimensional space in which gravity is present, pulling objects inward. If I had a theoretical, say, baseball right here, out in space, and I let it go, it gets sucked into the Earth because of this gravitational field that's three-dimensional, represented by these arrows. And the number of arrows I draw here is not important. I could draw 4 or 5 or 6 or 8 or 10. I could draw an infinite amount of arrows because this gravitational field fills the entire space, three-dimensional space surrounding the Earth. Direction is important. It shows that the gravitational field is pulling inward. It would exert a force, an inward force towards the Earth on an object that is in this field. The closer spacing, if I had this baseball and I let it go, it would fall towards the Earth. It would accelerate towards the Earth, and the force on the ball would get greater and greater the closer and closer I would get to the Earth, based on the equation that I showed you at the top of the page, or on the previous page, F equals gmm over r squared. Gravitational fields follow this inverse square law, and by that what we mean is the r squared in that denominator of F equals gmm over r squared, the field gets very strong, inversely proportional to the square of the distance from the Earth as you get closer. Or in other words, if you doubled your distance from the Earth, let me write the equation down, F sub g equals g m1 m2. I usually use a capital and a lowercase. You don't have to, over r squared. In other words, if you double your distance from the Earth, your force of gravity would decrease by a factor of 4 because you're dividing by the square of the distance. Once again, r stands for distance, not for the radius of the Earth. It's how far you are from the Earth's center. All right, let's give you an example problem. Calculate the force of gravity between the Earth and the Sun. If the distances are given, how far the Earth is. The average distance of orbit is 1.5 times 10 to the 8th kilometers. Mass of Sun is given, mass of Earth is given. So the Earth and the Sun pull on each other. And if I said, okay, which one pulls harder, our gut reaction might be, well, the Sun pulls harder on the Earth than the Earth pulls on the Sun. But once again, according to Newton's third law, they both pull equally on each other. F sub g, that's F sub g. They pull on each other with this force, F sub g, equals g m1 m2 over r squared. They pull equally on each other. It's just that the smaller mass, the Earth in this case, is affected more greatly by this force than the Sun is. It actually turns out that the Sun does wobble a little bit based on the planets pulling on the Sun, but it's not that noticeable in most cases. We're going to ignore that right now. All we want to do is calculate the size of this force, which is just a kind of a plug and chug at this point. F sub g, the force of gravity that each of them pull on each other, is g, which is going to be given to you, 6.67 times 10 to the negative 11th. That's on the previous slide in the notes. Times mass number 1. Now once again, I usually use a capital and a lowercase mass. It doesn't matter. You can use two lowercase m's. But usually there's one bigger mass and one smaller mass. The order is not important here because of the commutative property of multiplication. But the mass of the Sun here, I'll put first, 1.99 times 10 to the 30th times the mass of the Earth, 5.98 times 10 to the 24th. These are all kilograms, standard units. You need to have standard units, divided by the distance from their center to center squared. Once again, these numbers that are published, doesn't state that here, but it's implied that that always means center to center as published. In this case, it's 1.5 times 10 to the 8th kilometers, but I want meters, so that's 10 to the 11th meters, because kilo is 10 to the 3rd, 3 more zeros, 10 to the 3rd times 10 to the 8th is 10 to the 11th, total meters squared. And don't forget to square that when you plug it into your calculator. So if you do plug that into your calculator, and you might want to practice that, it comes out to be 3.5 times 10 to the 22nd newtons. So the Earth and the Sun attract each other with that force. Just that the Earth has the mass, a smaller mass, so it's pulled into orbit around the Sun and not vice versa. Once again, you might want to pause the video here and practice that calculation, because you can easily make a mistake with all the exponents and the big numbers here, just to make sure you can do that when it comes to the homework. Alright, we have an obvious not to scale diagram here. A person standing on the Earth. Calculate the force of gravity between them. They're pulling on each other. And once again, they're pulling on each other equally. It's just that the smaller thing, us, a person, or anything compared to the Earth, essentially on the Earth, is smaller than the Earth, insignificant in size, but we can calculate the force of gravity. We pull on each other. Those are supposed to be the same length. Force of gravity, pulling on each other. Calculate that with Newton's law of universal gravity, G m1 m sub 2 over r squared. So the force of gravity here on the person would be 6.67, and the force of gravity that the person pulls back on the Earth, 6.67 times 10 to the negative 11th, times the mass of the Earth, which is the 5.98, times 10 to the 24th, times the mass of the person, 75 kilograms, divided by the radius squared. Now, on first glance, you might think, well, how far am I from the Earth? I'm standing on the Earth. So I have zero distance. But once again, remember, this distance is measured from the center of the Earth to the center of the person. Now, the radius of the Earth would be from the center of the Earth to the surface of the Earth, which is given here, 6.37 times 10 to the 6 meters. And then from the surface of the Earth to my center, which would be another meter, would be insignificant compared to the 6.37, which is basically 6,370,000 meters. If I tried to add one more meter to that, it would not make any difference. You can try, but it will not make a difference. So the effective distance from center to center is the radius of the Earth, 6.37 times 10 to the 6th. That's in meters already, so we're good. And don't forget to square that. The force of gravity here then is, if you plug that all in, and once again I would recommend that you even maybe pause the video right now, do the calculation, see what your answer is, and see if it comes out to be my answer, which came out to be 737 newtons, standard units. Force of gravity. The Earth pulls on me with that force, I pull on the Earth with that force. I'm small enough so that it makes a difference to me, but it makes really no difference to the Earth. It would cause me to accelerate if I jump up in the air. It would cause me to accelerate downward at 9.8 meters per second squared, and the Earth would not be affected by this force at all, essentially. Insignificant amount. Now, if you remember back last week, or last month, we could have taken a shortcut in this problem. And that is, we could have used the equation W equals mg. Because weight is the force of gravity on an object. On the surface of the Earth, we know that g is 9.81 meters per second squared. In other words, the weight of a person, the force of gravity on a person who's 75 kilograms, is 75 times 9.81 meters per second squared. So the weight comes out to be 736 newtons if you calculate using this equation, which is essentially the same as 737 newtons. This is the shortcut method. This only works, however, if you know the acceleration due to gravity, in this case 9.81, which we know on the surface of the Earth, but now we're going to do a lot of problems where you're not on the surface of the Earth, or things are separated by great distances. But just want to show you here that this is consistent. It was kind of overkill to use Newton's law of universal gravity here to calculate the force of gravity on this person, but it's very restrictive in that W equals mg can only be used when you know the acceleration due to gravity, in this case 9.81, but it is consistent. So to recap, gravity is universal. Everything has gravity. Everything has a gravitational field that you could draw like that first or that second diagram on the first slide. You can calculate the force between any two objects by using F equals gmm over r squared. You could use this to calculate the force between Jupiter and Venus. Those two planets are pulling on each other. You could use that to calculate the force between a baseball and Mars. They're pulling on each other. Any two objects anywhere in the universe are pulling on each other. Gravity is universal. And it follows the inverse square law. When you double the distance between the two objects, the force of gravity goes down by a factor of 4. If you triple the distance between two objects, it reduces the force of gravity between those two objects by a factor of 9 because it's inverse squared. 3 squared is 9. If you increase the distance by a factor of 5, the force goes down by a factor of 25. It's an inverse square law, and it's universal.